Okay, I guess it's a time. So good morning, everyone. Today we have a first speaker, Yu Chen from Northwestern University. So he will talk about wall crossing for K-modular space. Please, yeah.
Okay, thank you very much for the invitation and introduction by Professor Deqi Zhang. So today I want to talk about K-modular spaces of log funnel pairs and their wall crossing phenomena. So first of all, this is joint work based on joint work with Kenny Asher and Christine de Fleming. Also involves some other joint work with Chen-Yang Xu, Ziquan Zhuang, and Harold Bloom. So let me recall the idea of K-stability. So throughout the talk, we work over C. And then funnel variety, or more generally, log funnel pair. So let's say this is my XD is a log funnel pair. If I have the following, so if X is normal, projective, and then D is effective Q divisor. Such that if I look at the anti-canonical divisor of the pair, so minus KX minus D, this is ample Q criteria. And most of the time, we will restrict ourselves to KLT pairs, but at this point, I think we can assume it's just normal, and K-stability would automatically imply it's a KLT pair. And then the idea of K-stability come from this Yelchin-Donaldson problem. Is an algebraic theory to characterize the existence of K-line time matrix. So K-line time matrices usually are defined over funnel manifold. That is a smooth funnel variety where your divisor is 0. And then if you have a non-zero divisor, that just means you allow some cone singularity. So sometimes it is also called conical K-line time matrix. So if you have a coefficient C along a divisor, then that just means the angle, the cone angle you allow will be 2 pi times 1 over, sorry, 2 pi times 1 minus C. So coefficient is C is the same thing as saying this cone angle is 2 pi 1 minus C. So as you see that if I don't have a divisor, then the metric will be regular. Okay, so now we know that the Yelchin-Donaldson conjecture is a theorem, and then we can sort of completely use K-poly stability to detect the existence of K-line metrics. But the algebraic theory of K-stability aims to find the effective way to check this definition, which is originally very complicated definition, but now we have some really powerful tools to check this stability condition. So let me introduce first of all this evaluative criteria of Fujita and Lee. So first of all, we give a bunch of definitions. So suppose I have a log funnel pair. And then a divisor E over X is given by a prime divisor E inside Y, and this Y is birational, a birational model or a resolution over X. And we always identify a divisor on a birational model with its string transform on some even higher birational models. And then once you have this divisor, you can define two invariants. So you have the log discrepancy function. So that is just, I use this notation, capital A, to represent log discrepancy. It's just the usual log discrepancy that we learned in birational geometry. So you look at the coefficient of ky minus the pullback. So if I call this map mu, then I look at this relative canonical divisor. And then it has the coefficient along E and I plus 1. So this is my log discrepancy function. And then the next one is called the expected vanishing order. Sometimes also called S invariant. So this is just defined as an integration, but first of all, I need to rescale by the volume. So here n is the dimension of X. And then I integrate to infinity the volume of the pullback of anti-canonical divisor, which is ample on X and becomes big enough on Y. And I just twist it by T times this divisor E dt. So as you see that as T becomes larger and larger, the section of this line bundle or a multiple of this divisor will be smaller and smaller, and eventually will go to 0. So although I'm writing here as an integration to infinity, but actually this is a finite integration. And it will stop at the so-called pseudo-effective threshold. Okay. So once I have these two invariants, I define this this beta invariant. So which was first introduced by Kento Fujita. It is just the difference of these two invariants. So this A is the invariant coming from singularity theory, and S is an invariant come from section or volume of divisors. Okay, so then the evaluative criterion of Fujita and Lee gave us an equivalent way to characterize K-stability. So let me state their theorem. So the first part is due to Fujita and Lee. This is Lee is the Chi-Lee complex geometry at Rutgers. So what they show is this pair is K semi-stable if and only if the beta invariant is always positive, sorry, non-negative for every divisor E over my final variety X. Okay, so in other words, the original definition of K-stability requires the checking of the Futaki invariant, which is closer in spirit to geometric invariant theory. But this new criterion sort of replaces the role of Futaki invariant by this new invariant, which is closer and more compatible with the techniques in birational geometry. And then we also have a criterion for K-stable. So this pair is K-stable if and only if the beta invariant is positive for every E over X. Okay, and 3, if we want to characterize K polystability, which according to Yalchin Donaldson is the algebraic condition that is equivalent to the existence of K-Lison matrix, then you will need something, I think, slightly different. So I don't think it can be directly tell from evaluative criteria without some work about the automorphism group. So I will state this result of Li Wangxu, although there may be some other equivalence versions. So XD is K polystable if first of all, it is K semi-stable. So K polystable implies K semi-stable, and every K semi-stable degeneration of XD is itself. So in other words, K polystable plays a role as like a closed point in the moduli problem. So it can't degenerate to something that's different, assuming semi-stability. Okay, so these are the definitions, and from these definitions, it's not obvious that we can use this to form a moduli space. But turns out K stability is really, I mean, after all of this works in recent like 10 years or so, it becomes clear that K stability is really maybe the best way to construct a moduli space.
Sorry, Yuchen, to interrupt you. You say it's a definition, but it's written as a theorem. So 1, 2,
yeah.
3 is if only one direction. So it is.
Yeah.
So is the definition is a theorem? Or...
Oh, okay. Here, yes, it is if and only if.
Yeah.
Thank you. Yeah, thank you. So yeah, I don't want to give the original definition because it's somewhat involved and perhaps also not so easy to use. But this evaluative criterion is really easy to use, and we will see later some examples. Okay, so you can take this evaluative criterion as a definition, and then we will proceed from here. So next, I want to state this so-called funnel K-moduli theorem due to many people. I will try to list them. So Alper, Bloom, Harper, sorry, I will try to go as alphabetic order. So Harper, Leitner, and Lee, and myself, and Patak Favi. Oh, sorry. Again, there are too many people, so it's very easy to HJ. So I should put Chen Jiang here. Yeah. Palafavi, and I think Xiaowei Wang, and Miao Xu, and Zixuan Zhang. Okay, it's possible that I missed someone, but I think this is at least 90% correct. Okay, so let me state the theorem. So the idea of the theorem will be that I fix some numerical invariance. So I fix the dimension n, dimension x equals n, and the volume, which is just the anti-canonical divisor. You take the self-intersection to be v. So these are some numerical conditions, and then also we fix the coefficient to be c. So you should think about this coefficient as a coefficient set. Maybe I should write a coefficient set rather than coefficient. So I fix I fix the rational number C, positive rational number, and then I allow multiplicities. Okay, so then there exists so-called Artin stack of finite type, which we denote by this curly M VC K, parameterized parameterizing K semi-stable log final pairs. X, T. Moreover, this stack admits a good moduli space, and it's actually a projective good moduli space. Which we use the Roman letter M. And this good moduli space parameterize K polystable log final pairs. So in some sense, if you restrict yourself to the polystable ones, those carries K-line symmetrics, then they do form a moduli space, and this moduli space is a projective scheme. So in some sense, without this K-stability condition, it's almost impossible to construct a general moduli space, because even for the simplest final variety P2, it has so many degenerations to singular del Pezzo surfaces. And even for smooth ones, you have many isotrivial, but isotrivial degeneration with the different fibers. So that made the moduli problem behave really, really strange. And then adding in this stability condition sort of remedy those pathological phenomena. Okay, any questions? So if no question, let's move on. So today I want to discuss the behavior of these K moduli spaces when you change the coefficient. So this is what we will call walk-crossing. So the idea of walk-crossing is I start from let's say I start from some given final variety or a class of final variety. So let's say X is a final variety. In some bounded family, for instance, you can take a projective space or some final hypersurface of a given degree and dimension, let's say in a bounded family. And then I look at the divisor D, which is proportional to some multiple of the canonical divisor. So here my R is some positive rational number. For example, we can start from X to be a projective space, and then D to be inside Pn is a hypersurface of degree D. So here I let my D to be, this is a Weil divisor. And then later on I will add a coefficient to it. So then I can consider this pair X comma D with a coefficient C. So notice that D is an integral divisor, and then my C is some coefficient that change the pair. So this is a log final pair if my C belongs to the interval 0 and minimum 1 to the inverse of R. Okay, so therefore, now you have a bunch of pairs, X and the divisor D, and this coefficient is changing. And then, as you know, that in the definition of K-stability, we have this beta invariant, and it actually depends on the choice of C. But fortunately, because of this proportional condition, which is important in our work. So if you don't have this proportional condition, a lot of the result may look different. But with this proportional condition, it's easy to see this is a lemma that for a divisor E over X, we always have this function C maps to beta invariant of E with respect to this pair X comma CD. So you're changing the coefficient on your boundary divisor. This is always linear. Or maybe I should say affine. Because linear may be misleading. So let me say affine. So in other words, it's a polynomial of degree 1. Okay, so therefore you see that the K semi-stability or K stability is equivalent from this evaluative criterion to the positivity of beta. And you know that beta is affine in C. Therefore, once you know that I have two coefficients like C1, C2, such that beta are positive or non-negative, then everything between them is also non-negative. So therefore, we have this interpolation result for K stability or semi. Let me just write semi-stability. So if I know that X comma C1D and X comma C2D are both K semi-stable, then so is everything in between them. So this is very nice because then at least I know that for example, if my final right is a projective space, then you can choose your C1 to be 0. And then Pn we know is a K polystable. So at least on the one side, you have something that is K semi-stable. And the other side, you can see that the interval or let's say the collection of coefficients that made this pair K semi-stable is always an interval. And then you have like some possibly largest coefficient C, such that this pair is K semi-stable. It's similar to the idea of a log canonical threshold, where we call this K semi-stable threshold. Okay, so then a very simple example tells you that you can't expect that this K stability is independent of C. This is just a very easy example, maybe the first example one can compute. So we consider P2 and the coefficient C times Q, which is a conic. So Q is a smooth conic. Then this pair, this log funnel pair, is K semi-stable if and only if my C belongs to this interval 0 to 3/4. And then it is K polystable if and only if my C belongs to the open interval 3/4. So somehow, by the way, this is due to the work of Chi Li and Song Sun. So as you see that it is log funnel for every C from 0 to 1, right? Because my conic is O2 and the canonical divisor P2 is O minus 3. But you can't really go to 1. You have to stop at the 3 over 4. And then what happens after 3 over 4 is you need to replace this pair by its polystable degeneration. And the polystable degeneration, so K polystable degeneration here at 3 over 4 is this degeneration that replaced P2 by this cone P114. And then under this degeneration, your conic will become a section of the cone. And then turns out this cone together with the section at infinity with coefficient 3, 4 is K polystable. Okay, so this is perhaps the first example of a wall crossing. Okay, any questions? All right, so let me move on. So next, I want to state this wall crossing theorem due to Asher, De Fleming, and myself. Also, later, Chu Yuzhou gave a generalization of our theorem. So we show that there exists a bunch of walls. So under this, under the notation above, there exists a bunch of walls. So CI, and the main point here is this CI is a finite collection of walls. So you won't see like infinite many walls. There's finitely many walls, such that so if I look at the K moduli stack, so here I ignore this N and V. I just look at C, and then I guess under the notation, I just means this proportional condition, proportionality. And maybe you can replace the right-hand side by the minimum of R inverse with 1. That's okay. Sometimes it even stops before that. But anyway, so what I want to say is this moduli stacks and also the moduli space are the same for my choice of coefficient within the interior of each interval, or you can think about these as chambers. So all of these finitely many walls divide this big interval into smaller intervals, and then inside the interior of each chamber, this moduli space remain the same. And moreover, if you move from one chamber to an adjacent chamber, then we have this wall crossing diagram. So so let's say you start from something slightly less than a wall CI, and then on the right hand side you have this you pass the wall, and then in the middle you have things on the wall. Then you indeed have two open immersions, and then this open immersion are on the stack level. So these are stacks, and then on the space level, you do have some projective morphisms. So this is on the space level. And then here, all of these are open. And then downstairs, these are projected. And also, we establish a local slice theorem based on the work of Li Wangshu on this wall crossing. So we show that a tau locally it is a variation of GIT. So globally, it may not be a variation of GIT, as K modular in general is not. I don't think you can always write it as a GIT quotient, but this idea of good moduli space pretty much is like abstraction of or like a gluing of alpha and GIT quotients. And in this case, if you're changing coefficient, turns out this good moduli space also behaves like a variation of GIT, at least locally.
You can, sorry to interrupt you. So your M is a semi-stable one or stable one? The modular space.
Oh, good point. So, so this curly M, these are the semi-stable ones. And this capital, this Roman M, they are polystable.
But then you say they are the same, so I'm confused. So,
sorry, I shouldn't say they are the same. So let's put it this way. So they are independent of the choice of C. So in other words, I can freely choose my C in each interval. But
I understand. Yeah, I see. Okay. Yeah. So independent of C. I see. Okay.
Independent of C. So they are not the same because usually it's very easy to come up examples where you have semi-stable pairs but not polystable. Actually, this earlier example give you that for 3 over 4.
Okay.
Yeah.
Okay.
All right. Any other questions? Okay. Good. So this is a general result toward the K-modular wall crossing. But then, what can we say about some explicit case? Like I was just telling you about this example of hypersurface inside projective space. And turns out in this case, even in P2, there's some interesting story happening. But let me first state a general result for Pn. So this is due to Gallardo, Martinez Garcia, and Spotty independently due to myself and Asher de Fleming. So what we show is okay. So let me fix the notation. So let MCK, this curly MCK, and this capital MCK. Or okay, maybe I just ignore the stack case and let's just work with modular space. So let this modular space MCK be the closure, of the locus Pn with C times D in the K modular space. Okay, maybe you want to fix the degree as well, but let me just save my notation. So with a fixed degree. Equals D. So if you write it rigorously, maybe you should keep track of N and D as well, but let me just try to be simple. Then we show that at least when C is very small, so I put epsilon here to mean that epsilon is very small. Then this K modular space is isomorphic to the GIT of hypersurfaces. So in other words, the starting point of these modular spaces as hypersurfaces, but we treat it as boundary divisors inside Pn, then the starting point of this wall crossing is nothing but the GIT. So in other words, the major contribution still coming from Pn. Okay, so therefore it gives us at least one end of this wall crossing chain. But what about the other end? So the other end usually is very difficult to figure out. But at least we can say something for some examples. So let me give you one example of what's going on with plane curves. So I guess I will do this case maybe. So d equals n equals 2 and then d equals 6. So in this case, we are talking about plane sectic curves. And then, as I said, right, so when C is very small, we have this K moduli space is isomorphic to GIT. But this can be true for C becomes larger. For example, I know that I can take this very special curve. So 3 times Q. So this is called the triple conic. So from earlier, when I explained this result of Li and Sun, you see that this conic will destabilize at coefficient 3/4. So here I take the divisor to be triple conic. That means it should destabilize at coefficient 1/4. But this triple conic, it is indeed a GIT, a polystable inside the GIT of a plane sectic curve. So therefore, we see that C equals 1/4 is a wall for such moduli space. And what happens is here you have your P2, and here you have a triple. Let me try to draw it. Yeah, it's kind of hard to draw, but so this is your triple conic 3Q. And then it is a K semi-stable, it is K polystable actually at the coefficient 1/4 minus epsilon. And then at the coefficient 1/4, it degenerates to this cone, which is P114. And then your triple conic will become a triple section. And then, so this is what happens at the C equals 1/4. But you can keep increasing your coefficient, right? Because your coefficient should be C belongs to 0 to 1/2, because your curve is like the anti-canonical divisor times 2, right? So your coefficient can go to 1/2. And then once you cross this wall, you will see the other wall crossing, which becomes an extraction. So it will extract a divisor in the moduli space. So what goes on is my underlying surface remain the same. It's still P114. But then now my curve becomes like a triple section. It looks like this. And because plane sectic curves, they're interesting not only like as plane curves, but also you can take double covers. So once you take double cover of say a smooth or ADE singularity plane sectic curve, you get a K3 surface. So therefore, all of these K moduli spaces are directional to the moduli space of this K3 surface. And this K3 surface are indeed generic degree 2 K3 surfaces. So then what we show in this case is in the plane sectic curve case is that this C1 equals 1/4 is the only wall crossing for plane sectic curve. And then if I draw this wall crossing diagram, I start from this this M GIT, which is my M it's isomorphic to okay, so let me write it as epsilon very small. And then this is the same as sorry, this should be K moduli. Yeah, this should be K moduli. And then I increase up to 1/4 minus epsilon, everything stays the same as GIT. But then at 1/4, you have a wall crossing diagram like this. And this is like birational. And turns out that this map here on the left-hand side is an isomorphism on the level of moduli spaces. So it only replaces this point in the moduli space representing the triple conic by this P114, by this pair. So P114 with the triple section. But on the other side, you have the freedom to choose which direction you want to deform out your triple section to some triple cover of this section, this P1 here. And then this is, turns out this is a weighted blow up of curve type. Okay, and at the end, you get 1/4 plus epsilon, and we show this is only wall crossing, so which means this is the same as you go to even 1/2 minus epsilon. But this moduli space is also interesting because we know that K moduli spaces are I mean, K stability implies KLT singularities. So therefore, every pair X comma D in this moduli space satisfies that the log canonical threshold of this pair is at least, so it's bigger than 1/2 minus epsilon, but actually it is at least 1/2, pretty much follow from the ACC of log canonical threshold. So therefore its double cover let's call it Y, is semi-log canonical. So in some sense, this K moduli space at the end also give you something interesting, and not from the GIT point of view, but perhaps from the KSBA point of view, or even from the Hodge theoretic point of view. So actually, this moduli space has been worked out by many people before us. So it was a result by Shaw and later by Lu Yangang. They just tell us that the last moduli K moduli space where the coefficient almost hit the Calabi-Yau wall. So this one is actually isomorphic to so-called F2 hat, and which is a small modification of the Belli-Borel compactification. So this is Belli-Borel compactification. And this map here is a small birational, and it pretty much just take this not the Lefschetz divisor, parameterizing these double covers of P114. So essentially, these are like an elliptic fibered K3, and then you shrink the section of the elliptic vibration. And then these divisors are not, this divisor is not Q-Cartier in the Belli-Borel compactification, so you sort of Q-Cartierize it. So this is some Q-Cartierization. And then they show that this, of course, is a weighted blow up. Let me just write blow up of the GIT. So somehow you can see that this K moduli gave you like a new interpretation of this theory that Shah and Luenga worked out. So, therefore, this sort of gives us some confidence of developing this theory to some more general setting. And then recently, we sort of did another case that, I mean, in terms of case resurface, this will be the second case, because I guess degree 2 case re is the simplest one. And then the next case will be degree 4 case re. So we work out the degree 4 case re, and the result is complicated, but it also solves like a conjecture of Laza and O'Grady. So maybe I can state in the next slide. So for degree 4 case re, we know that general one is a quartic surface. Inside P3, and then you can run this same game. So I let this MCK to be the K moduli, or let's say the closure of this pair P3, and then C times this quartic surface, which I call it S, in the K moduli space. So all of this MCK, they are birational to the moduli space of quartic surfaces. And then, as we saw earlier, this GIT equals K result still hold. So, so I still have this C very small, which can identify this GIT with the K moduli space. And then what we show last year with Kenny and Kristen is that we can describe this wall crossing in a very explicit fashion. So we show that there are 9 wall crossing. There are 9 walls for this game of surfaces. In P3, and then out of the 9 walls, there are 2 blow-ups, which extracts the hyperelliptic case rays and the unigonal case ray. So unigonal is just another name of elliptically fibered case ray with a section. And then the rest 7 are flips. And turns out all of this wall crossing were predicted. So this wall crossing predicted by Laza and O'Grady. Although their motivation was not case stability, but rather study the birational map from the GIT moduli space to the Belli-Borel moduli space. So on our picture, there's also the Belli-Borel. So where we have this M GIT, which is MK epsilon, and then there will be this 9 wall crossing, which I won't write it out. So to this last K moduli, and similarly, what you get here is pairs XD, where X1 minus D are K semi-stable, which implies this pair is log canonical, log Labial, such that X1 minus epsilon P is K semi-stable, or let's say K polystable. So then we show that there is also a birational map to the Belli-Borel. So this is Belli-Borel compactification for degree 4 case 3. And then this map is again some Q-caracterization of the two the left-shift divisors, which corresponding to hyperelliptic and unique case. So moreover, we can write this this K modular space. We can write this K modular space as some kind of approach construction. So it turns out this is approach of R represent the section ring of the interior of this Belli-Borel concatenation, which is I just write it as F4, and then the line bundle will be something like C times lambda Hodge. So lambda represent the Hodge line bundle plus 1 minus C times some divisor. And this divisor delta, so this delta K, turns out I can write it as my notes. Oh, okay, here we go. So it's 1/4 times HH. So this is the hyperelliptic NL divisor plus 9 over 8 HU, where this is the unique NL divisor. Yeah, so this sort of expression was conjectured to be finally generated by Laza and O'Grady, and then somehow by constructing this K modular space, we verify, not directly, but through this modular construction, the finite generation conjecture of Laza and O'Grady. So this implies. Okay, so I guess I will stop here. Thank you very much.
Thank you. Are there questions or comments?
So has anybody considered P1 with a bunch of points? Then you presumably you get like different compactifications, so M0 and bar, these things.
Yes, that's a great question. So for P1, you can put different coefficients, right? But turns out you don't really get anything new. So you can have P1, C1, P1 plus something like that, C, M, PM. Right, and turns out that this is this K stability is equivalent to GIT for a weight C1 up to CM. And I think a more general statement for hyperplane arrangement is worked out by Kendo Fujita. So he showed that the same is true for hyperplane arrangements. So in other words, if you have PN with a linear combination of hyperplane arrangements, then the K stability is equivalent to GIT for that particular. I mean, you just put your weight in GIT as the same as the coefficient of the divisor. So therefore, you don't see some new modular space. Yeah.
So my question is that you seem to, for low degree 3, 4, or conic or quartic already give a trouble. So is it possible to have a theorem, for say degree bigger enough, or I mean, not case by case to have.
Oh yes, that's a great question. So for plane curve, we have a result showing that the first wall always come from this conic. Yeah, so this we know. So plane curves of any degree.
I see.
So the first wall is always induced by, okay, so your degree is d, right? It's always induced by d over 2 times the conic, but that's the case if d is even, or d minus 1 over 2 times the conic plus a transversal line. So this is transverse line if d is odd. And you can compute the first wall explicitly. And we also show that the first wall is always a weighted blow-up. So in higher dimensions, I think a reasonable conjecture is a similar thing holds. So the first wall should always be induced by multiple of quadric hypersurface. But I don't think we know how to prove that. Yeah, it turns out it's quite difficult to, in higher dimensions, to describe the wall crossing.
Thank you. Yeah. Are there any other questions?
So if you take the coefficients very close to this Calabi-Yau bound, and also so you have the K final moduli, and on the other side you also have the KSBA moduli, which is also a K moduli. Can you compare these two?
Yeah. That's another great question. Actually, I plan to say something about it, but it sort of lost track of it. So yes, we expect that there is something sitting in between this last final K moduli and the first KSBA module. So the conjecture will be in the general case, right? You have M R inverse minus epsilon K, and then on the other side you have this M R inverse plus epsilon KSBA. So assume you have a reasonable class of variety to start with, for instance, hypersurfaces in Pn or things like that, so that these two moduli spaces are closure of a common locus so that they are birational. Let's say they are birational. Then the conjecture is that there exists some Calabi-Yau moduli space that sit in between them and then serves as the base of this birational. So it turns out that this conjecture is pretty challenging, even for plane curves, but recently we found a solution to it. So this is still in progress with a lot of people, which I can't name all of them, but my two co-authors, Kenny Asher and Christine de Fleming, are in here, and also Harold Bloom, Dory, Bailey, Giovanni Inchiostro, and Xiaowei Wang. So there are 7 people in this paper, and what we show is this MCY does exist for plane curves. So the difficulty of this this conjecture is, if you want to construct some moduli space, you better start from some moduli stack, parameterizing some reasonable pairs, right? And then you try to quotient. So this stack usually is some quotient stack of something in the Hilbert scheme, and then you try to identify different objects through the so-called S equivalence condition. But for Calabi-Yau, the only reasonable condition one has in this case will be just require this pair to be log canonical or semi-log canonical. But if you require only this condition on singularities, the boundedness fails. So a modular problem without boundedness is like people walking without legs. so therefore this really put a big obstruction. But at least in this case, for this very special plane curve case, we found a way to get back some boundedness without changing much the modular problem. So, and this is the way we eventually, for this special case, we solve the conjecture. But in general, I think it will be really interesting and hard question. Yeah.
Okay, thank you very much for the very nice talk. Should we thank the speaker now? Yeah.
Okay, thank you.
Yeah. Maybe we take a 15 minutes break as usual. So we start the second talk 15 minutes late. That means 10:15 here in Singapore. Okay. Okay. Yeah.